Okay, let's see. So I think I want to try to make this a bit of a shorter class. I just want to tell you what the scarf complex is, how it works, maybe prove one or two things, but but basically just tell you the general idea of how this goes. Okay. So we start with a monomial ideal, right? M1 up to Mr. So we make the scarf complex, which we call delta sub I. And that's why I didn't like my notation from last class, because I really want delta sub I to be the scarf complex. So the vertices, you have one vertex for each monomial. Okay? And then the faces are going to be the subsets F such that the least common multiple of that set is unique. So let's see an example of this. So this scarf complex, delta I, is going to have 4 vertices, right? And I could label them 1, 2, 3, 4, but actually I might as well label them by their names, which are the monomials. Right? So here's x squared, xy, z squared, and y squared z. Okay? These are the 4 vertices. Now, what are the edges? Well, for example, I claim that I need to put an edge between these two guys. Why is that? Because this edge would be labeled x squared y, right? That's the LCM of these two things. And that is the only way that you can get x squared y as a least common multiples of things over here. So the LCM of x squared and xy is unique. So that's why I put it in. So do you guys see an LCM that is not unique? So for example, what's the LCM of x squared and y squared z? Well, it's x squared y squared z. And the question is, can you get that LCM as the LCM of a different set? And you can, right? Because once you have these two guys, you might as well add x, y, and you're not going to change the LCM. Okay? So this LCM is not unique. And that means that I should not draw an edge between x squared and y squared z. Okay? And so basically for each set, you would do this. Okay? So if you do this, you'll see that the only way of getting x squared, z squared is these two. Here you get y squared, z squared in a unique way, x, y squared, z in a unique way, and x, y, z squared in a unique way. So those are the edges. And of course, you might as well label these edges by their LCM, right? So why don't we do that? Y squared z squared, x y squared z, x y z squared, x squared z squared, and x squared y. Okay. Now, what are the faces of this scarf complex? Well, they're going to be the triples of elements that have a unique LCM. So for example, what's the LCM of these three guys? It's x, y squared, z squared. And if you look at that, that's the only way to get that LCM. So I need to throw this triangle in. Okay. Now let's look, for example, at this triangle from x squared, z squared, y squared z. Should I put that guy in? Well, the LCM of x squared, z squared, and y squared z is x squared, y squared, z squared. And you can throw this guy in and get the same LCM. So that means that I should not put that triangle in. So you just have to do this carefully and see which LCMs are unique and which ones are not. And when you do that, you'll see that these two triangles are unique and nothing, and that's it. So this is the scarf complex. Okay. So is it clear how I'm building this guy? Does that make sense? Okay, so the first thing I'd like to do is actually give you a proof that this is a simplicial complex. Okay. So proposition, this thing is a simplicial complex. And its dimension is less than or equal to minus 1. Okay. So let's prove this. So I have two things to prove. So first, let's prove that it is a simplicial complex. So what does that mean? That means that if you take a face, let's say f of delta I, and now you take a subset of that, that should be in the simplicial complex. Now, of course, it's enough to prove that if you have a face and you take one element out, then you haven't left the simplicial complex. So if I prove this, I will have a simplicial complex. And so the way I'm going to do that is by contradiction. So suppose that G is not in here. So what does that mean? Well, you're in the scarf complex when your LCM is unique. So if G is not here, then that must be because the LCM of G is equal to the LCM of some H. Right? But now I'm going to do the following. What is M of G union I? It's the LCM of mg and mi. Right? If I want the LCM of the things in G union I, well, I take the ones in G and I take I. Right? So it's equal to the LCM of mh, mi, because mg is equal to mh, and by the same reason, this is the LCM of mh union I. Right? But what happens here? Well, G was obtained from F by taking out I. So if I add I back in, this is exactly M sub F, right? Sorry. The LCM of MH and MI is just MH union I, right? Okay. And so what I have is that M sub F is equal to M sub H union I. But by assumption, F is in the scarf complex, so its LCM is unique. So if MF is equal to M something, that something must be F. Okay. So F has to be H union I. So that means that there are two cases. Either H is equal to F minus I, or H is equal to F, right? These are the only two sets that when you add I to them, you get F. But if H is equal to F minus I, by definition, F minus I is G. So I get that H is equal to G, which is a contradiction. And if H is equal to F, then I get that MF equals MH, right? Because H is equal to F. But MH is equal to MG. And so I get that MF and MG are equal to each other, but F and G are not equal to each other. And again, that contradicts the fact that F is in the scarf complex, so because F and G are different from each other, MF cannot be equal to MG. Okay. So that's a little argument that shows that this thing is actually a simplicial complex. You guys have any questions about it? Okay, so how am I going to show now that the dimension of the scarf complex is at most n minus 1? Well, let's take a face. And let's suppose that its dimension is not less than or equal to n minus 1. So let's say that, I don't know, maybe I'll call this F1 up to Fk. And let's suppose, to get a contradiction, let's suppose that the dimension of this is more than n minus 1, meaning that k is more than n. The n minus 1 dimensional simplex has m vertices. So if I assume that this guy is more than n minus 1 dimensional, it has more than n plus 1. It has at least n plus 1 vertices. Okay? Now I say the following. I say, what is the label that I give to this face F? Well, by definition, this is just the LCM of MF1 up to MFK. Okay? Now remember that we're living in n variables. Right? So this guy I can write as x1 to the a1 up to xn to the an. Okay? And this is the LCM of more than n plus 1 things. Okay? So let's think about this. I have a monomial. It's the LCM of some things. Now, for example, where does the x1 to the a1 come from? Well, the reason I have x1 to the a1 here is because that is an exponent that I see in one of these guys. Okay? So I can, for sure, take this x1 to the a1 and say, well, that guy comes from this generator. And then I can take the next guy, x2 to the a2, and for sure that's going to come from this generator, one of them. Okay. And I take Sn to the an, and I say that guy comes from this generator. Now, if you see the way I did this, I just drew n arrows that go into this set. Right? Each one of these n exponents is contributed by one of the things here, and that means that only n of these guys get to contribute towards the LCM. But I have more than n guys. Okay. So that means that since k is bigger than n, there must be some, let's say, mfi that doesn't contribute to the label of this face. But then, what is mf minus fi? Well, if you take this LCM and you take out the monomial mfi, well, mfi wasn't contributing to the answer anyway, so you can take it out and you're going to get the same answer. Okay. And you get a contradiction because this was supposed to be a unique LCM, and I just produced it by two different sets. Okay. So that's how we know that we have a simplicial complex with dimension less than or equal to n minus 1. Okay. Here's kind of an easy proposition because, I mean, I told you that one way that you want to think about this is that the scarf complex is kind of analogous to that staircase diagram that we drew in 3 dimensions. So we said that in 3 dimensions, if your ideal was strongly generic, then this staircase diagram resolved it for you. And now we want to think if we're generic in this higher dimensional sense, then it's the scarf complex that is going to resolve you. And this makes this precise. If you look at the edges of the scarf complex, then every edge of the scarf complex is also an edge of the Buchberger graph. Okay. And if your ideal is generic, then actually this is an equality. So this is kind of a nice, easy lemma that basically says that this simplicial complex delta I is really very closely related to the Buchberger graph. In fact, in the case that interests us right now, when I is generic, then the Buchberger graph is just the skeleton of the scarf complex. Okay? This is a nice little exercise that I think you guys should do to practice with the scarf complex, so you can see how to prove things like this. Now, what I want to do, of course, is the following. So we started with our ideal. We define our scarf complex, which is a simplicial complex. And then we make a a chain complex out of this, right? And so that's called the algebraic scarf complex. Is just the Taylor complex of this delta I. And actually, if you compare the picture that I drew here with the one from your notes from the previous class, you'll see that this is exactly the example that I used in the last class. And we wrote out the resolution for this thing, right? So we said that it looked like two triangles, 5 edges, 4 vertices, like this, and we wrote down the gradients also, right? So it was 0, 0, 0, 1, 1, 0, 2, 0, 0. So these are the labels on the vertices. Then the labels on the edges are these. And then the labels on the triangles are these. Okay. So in that example, this is what's called the algebraic scarf complex. And the point is that this is the guy that you want to compute if you want to resolve your ideal. So let me write down a proposition here, which is that every free resolution of your ideal I contains the algebraic scarf complex as a subcomplex. Okay. And this tells you how natural this object is, right? Because in the way that I defined it, you might think that I just pulled this out of a hat and it's some magic trick, but actually this proposition tells you that in a way this scarf complex is just very, very natural, because no matter what free resolution you take of your ideal, this guy lives inside it. So it's kind of something that you can't avoid. It really lives inside any free resolution that you can think of. And well, the proof of this is not too hard, but you see it in the book. Okay? But the statement that I want to make is that if I is generic, well, let's see. So if I is generic, then the algebraic scarf complex is basically the best possible resolution. There's no question about it. This is what you want to do. The algebraic scarf complex is the best possible cellular resolution. Okay. How do I say that precisely? Let's say it in a theorem. So this theorem has two parts. Well, the first part is kind of clear, that the scarf complex is a subcomplex of the Hall complex. Now, this shouldn't be too surprising by what I'm telling you there, right? Because the Hall complex gives you a resolution, and I'm telling you that the algebraic scarf complex lives in there. So it's no surprise that you can always find inside your Hall complex, which we have been playing with, you can always find inside it the scarf complex. Okay? But if I is generic, then this is a much stronger statement. So if I is generic, then two things happen. One thing is that actually the scarf complex and the Hall complex are equal to each other. So that means that if you had a lot of trouble visualizing this Hall complex, well, now you have a much more combinatorial way of thinking about it. Okay? Because I'm saying if I is generic, to compute the Hall complex, you can just compute the scarf complex. They're the same thing. Okay? So come to think of it, this might be a way of doing the homework problem as long as I is generic, which I'm not sure if it is, but you should check. If you check, well, that would be a good idea to check your answer. Okay. But then the really nice theorem is that the algebraic scarf complex is, and maybe it's not too surprising that it's a free resolution, but what is amazing is that it's the minimal free resolution. Okay, this is the best one. And so this is kind of indisputably the best possible resolution because it's the minimal one. And not only that, but you actually have a simplicial complex that describes it for you, which means that if you want to understand the minimal free resolution, you translate everything into the topology and the combinatorics of the scarf complex. So it couldn't be better. Okay? So for example, in the last class, I gave you this example, and we talked about how this was a generic ideal, okay? And that means automatically, because this is the scarf complex of this generic ideal, automatically what I wrote down is the minimal free resolution. Okay? And that means that I have all the Betty numbers, I have all the growth theories, I have everything. Okay? So I want to make a double box around this because this is one of the nicest things that we'll see. So, for example, let's see. There's a corollary. If I is generic, then what's the Hilbert series of R mod I? Well, we have a free resolution, right? And so given this free resolution, we know that what we're supposed to do is just add these guys, subtract these guys, add these guys, subtract these guys, etc. And so what you get is the following thing. You get a sum over faces of the scarf complex of -1 to the number of elements in the face times the monomial of the face divided by the product of 1 minus the x's. Okay. So in this case, I can write the Hilbert series of R mod I just by looking at this picture. And it goes like this. First, the empty face is 1. Then you add you subtract the vertices. Then you add the edges. And then you subtract the faces, the two-dimensional faces. And you take all of this and you divide by 1 minus x, 1 minus y, 1 minus z. So this is the fine Hilbert series of this ideal. Okay? Of course, the answer is long, but we know that fine Hilbert series are always long. Now, one thing you might remember is that in the methods that we've used before, when you had to compute these things, there was a lot of cancellation. And, right? Things added, subtracted. But the fact is that actually here there's not going to be any cancellation. Why? Because by definition, each face has a unique label. Right? So there's going to be absolutely no cancellation. So this is the shortest possible formula you could hope for. It's a formula with no cancellation. With no cancellation. This is the shortest formula for the numerator. You just write it out. Okay? And if you want to know the Betty numbers, well, basically you just have to see whether there's an I-dimensional face with this name. 1, if there is an I-dimensional face labeled x to the a, and 0 otherwise. So that's it. So basically that means if you have the scarf complex, I mean if your ideal is generic, just do the scarf complex and you're done. Okay. Now of course it takes some work to compute the scarf complex anyway, but at least everything is reduced to doing that. So so that's what you do in the generic case. Just scarf complex, that's it. Now, what if you're not generic? Yep?
So you're saying that the scarf complex is simplicial.
Uh-huh.
It's a subcomplex of the whole. Does that mean the whole just has to be all simplified?
No. And we've seen examples of if you trust your homework. So if you trust the picture that I saw on your homework, and I think on most of your homeworks, then you will find that the Hall complex is not simplicial. And the scarf complex is simplicial. Okay? So that must mean that from the Hall complex to the scarf complex, we have to throw out all the faces that are not simplices. So we just proved that I is not generic, because if I was generic, then the scarf complex and the Hall complex would be equal to each other, and therefore be simplicial. So that means that you don't have another way of doing the homework like this. But yeah, exactly. And again, remember how this goes. If you choose a random ideal, it's generic. But if you choose one that you find in the exercises in the book, it's probably not generic because they're trying to make you work harder, right? And because I mean, of course, the point of the exercise was to illustrate what you do, and in one of the homework you have to deal with a non-generic ideal. Okay? Let me show you a different way to deal with a non-generic ideal, and this will be a way to check some of your answers. Okay? So what if I is not generic? Well, we do the same thing as with the staircases. You just move things a little bit to make yourself generic. So I not generic. Then we deform into an ideal that is generic. Okay. Then we take the scarf complex of that guy. And then we undeform. Is there a better word for undeform? It's kind of an reform. I don't know. You can choose what sounds nicer to you. This gives you a resolution, simplicial resolution. So maybe what I'll do for the rest of the class is we'll do this in an example, and then I'll just state the theorem that says that this works. Okay. So this example is not good enough for us because this is generic, right? So let's choose a different example. So for example, here's a nice ideal that is not generic. So how can we see that this is not generic? You can see, for example, that these guys are an edge of the Buchberger graph, and they have the same x-exponent. So that's one way of seeing that. So what happens when we I mean, let's pretend that we don't know this, and we just follow through and we try to compute the scarf complex. Well, the scarf complex is defined anyway. Okay? So let's see what this scarf complex looks like. Okay. Now you've probably also noticed that there's kind of an art to figuring out how to draw these things, right? Sometimes you draw them and then you can't see anything and you have to redraw them. So I don't know, I feel like probably what we want to do is something like this, just for symmetry reasons. So let me try to draw it like this and then see if I need to move things around or not. Okay? Those are the vertices. Now, I don't know, can someone tell me an edge of this thing? This is an edge. Its label is x squared z, and it's the only way that you can obtain that thing. Okay? Now, of course, we have a lot of symmetry. So if that's an edge, then this whole hexagon has to be in there. Right? So these are labels x squared y, xy squared, y squared z, yz squared, and x z squared. What about the other edges? For example, this edge, should I put it in between xy and xz? Well, the LCM of xy and xz is xyz, which is also the one I get for this edge and for this edge. So those are not unique, so I shouldn't put them in. Okay, so I don't put these guys. What about the diagonals? X squared to yz. Well, that thing, the LCM is x squared yz, and you can add xy without changing the LCM. So I shouldn't put the diagonals either. So that's it for the edges. What about the triangles? Huh? I can't have triangles, right? Why? Because I proved that this is a simplicial complex. So if a triangle is in there, then all its edges have to be in there. But you don't see any triangles in this picture. So there can't be triangles, there can't be tetrahedra, that's it. Okay? So this is the scarf complex. And it doesn't look like these other things that we have drawn, but that's not too surprising because this thing is not generic. So what do we do? What we do is that we deform. And here we have a lot of freedom. And depending on what we do, we're going to get a different picture. Okay? But let's talk about this. What's kind of the simplest way to deform so that the picture looks the nicest? Well, the issue is that these two x's have the same exponent, these two y's have the same exponent, and these two z's have the same exponent. I have no problem with these twos, right? Those are unique exponents. So let me keep the twos. They're not a problem. And then here is where I have to change things. Now what's a nice way of changing these exponents to solve my problem? There's many ways. But I mean, and you could change all of them, but I think the cheapest way is you have to at least change one of the x's, one of the y's, and one of the z's. And so let's do that, okay? And I think I'm actually going to try to, it scares me a little bit, but I'm going to do it anyway. I'm going to do it differently from how I did it in the notes so that you can have two examples. Scary, huh? So, but I kind of want, I don't know, I like symmetry, and there's symmetry here. So let me at least deform to the same number. So let's deform to 0.9. Okay? So let me deform this guy to 0.9 and leave this one alone. Let me deform this guy to 0.9 and leave this one alone. And deform this one to 0.9 and leave this one alone. Okay. And now let's try this again. I'm going to need your help now. Don't let me make a mistake. Y squared, z squared. This is y to the 0.9z, and z to the 0.9x. Okay. And now I should have more edges because this should, well, I should have more edges. So what edges do I have? X, y, z to the 0.9, you mean this edge? So is there any other way that I can get x, y, z to the 0.9? I think that's good. I can't add the x squared, or the y squared, or the z squared. And if I add this guy, I'm going to ruin the z exponent. So that's an edge. And by symmetry, again, I mean, this is why I want to do it symmetrically, because once I do part of the work, I get the rest of the work done for me. So by symmetry, this is going to be x to the 0.9 yz, and this is x to the, x y to the 0.9 z. Did I make a mistake? Did I make a mistake somewhere?
So the least common multiple of the ones on top, isn't it x to the 0.9 and y and z to the 0.9?
No, because the least common multiple of x and x to the 0.9 is x. Yeah. Okay, and how about these guys? Well, this is x squared y. This is x to the 0.9 y squared, etc. Now, what about those triangles? Should I fill them in? Well, you have to look at it carefully, but actually you do have to fill them in. For example, what's the label of this triangle here? It's the LCM of these things. It's x, y, z. Right? The LCM of these three guys is x, y, z. And you can't throw in anything additional because you're going to make an exponent bigger. And similarly, this is what? X squared y z to the 0.9. I don't know. I think the green stuff is easy to compute. You just do this carefully and you see that this is it. This is the scarf complex. So this is the scarf complex of the deformation, right? Okay. And the point is that, by the way, it came out the same. It came out the same here as it did in the book and in my notebook, even though I chose different exponents. But if you look in the book they choose something different and they do get a different subdivision. But what's the point? The point is that now I just pretend that epsilon disappeared. I undeform, and what I get is a this guy is a simplicial complex because this guy is generic and this guy is the scarf complex. So now if I forget my little deformation, I can just do it back. I can just go back here, right? So I went from here to here, okay? And then I come back and add that additional structure that I see in there, right? So I add this and this and this and this and this and this. And the theorem says that this is going to be a simplicial free resolution of the ideal that you started with. So that's how you can do it for anything, any ideal, any monomial ideal. Okay.
Undeforming, we're just adding it.
Yeah, basically every time you changed from a number to a number plus epsilon, you just set epsilon back to 0. Or another way of saying that is yeah, just kind of take that picture and put it on top of the one that you started with. Okay? Because really what's always going to happen is that this is not a complete picture. This one contains it. And so what you do is that the stuff that's here, that's missing here, is what you put in.
So it's sort of the opposite of what happens in the staircase diagrams.
In the staircase?
There we had a burger graph that was too full,
and you kind of, yeah, you kind of.
When we deformed it, the edges disappeared. And now
That's right.
we're putting in stuff.
That's right. By the way, so it's an open problem, and you might be interested in doing this. It's an open problem to interpret this construction in terms of staircases. So in 3 dimensions, it's clear how this matches the staircase picture. And it's open to figure out how this matches a picture of n-dimensional staircases. No one knows. But it seems like it should still work. I don't know. Anyway, so theorem. It says that if you have a monomial ideal I, and then you deform it so that you get something generic. By just adding any small exponents to the vectors, to the exponents, in such a way that you end up being generic. Okay. Then if you take the scarf complex of this guy, then, and now what we're going to do is that we're going to define this thing to be basically what you get when you undeform. Okay, so this is going to be the same thing as this, relabeled, or in other words, undeformed. To set the epsilons equal to 0 again. Okay. Then, and it's a simplicial complex. And then the Taylor complex delta I super epsilon is a cellular simplicial free resolution of I of length less than or equal to n. By the way, why is the length less than or equal to n? Because I proved that the scarf complex has dimension at most n minus 1. So it only takes n steps plus the additional step to get to I. Okay. And so this is kind of the big theorem about cellular resolutions, is that basically for any monomial ideal, you can find a cellular resolution with simplices and of a good length less than or equal to n. By the way, here, in this case, this is always minimal. This is always a minimal free resolution if I is generic. If I is not generic, then this is not necessarily minimal. It's short, but it might not be the shortest. So this is, maybe I'll write that here. Not necessarily minimal.